Now, what if we look at two molecules that have the same atom that bears the acidic proton? Okay, so let's take a look at the structure of acetic acid here. We have OH bonds and we have CH bonds. Based on the atom rule, right, carbon versus oxygen, we know that oxygen is more electronegative, therefore it is going to be the more acidic site here, the OH bond. Okay, so that's why I've highlighted it in pink in both of these cases. All right, so then we have OH and OH. So which of these molecules is going to be a stronger acid? Well, we need the next rule here because they're the same atom. They're both attached to oxygen. So we move on to resonance. Is the conjugate base resonance stabilized? Okay, so let's draw the conjugate base. I'm going to abbreviate here CH3COO minus, right? The conjugate base will have lost a proton. CH3, and this will also have an O minus. Okay. All right, well, if there's resonance, that stabilizes, and therefore the base is weaker, and then the acid is stronger. Okay, so we look for our patterns of resonance. Are there lone pairs next to pi systems, or are there negative charges or positive charges next to pi systems? And there are in this case, so we have a lone pair next to a pi bond, so we can take our electrons and draw a resonance contributor that looks like this. And we have no resonance here. There's nowhere that we can move these pairs of electrons because this carbon is sp3 hybridized. There's no easy to move pi bonds or anything like that. So we have resonance. Okay, so resonance means more stable, right? And more stable means that it's a weaker base, right? Therefore, its acid counterpart would be a stronger acid. Okay, so that means that this acetic acid is a stronger acid than methanol, right? And in fact, if we look up the pKa's, we find that the pKa is around 5 for acetic acid and the pKa is around 16 for methanol. So if resonance is present, it stabilizes the conjugate base, making it weaker, and therefore my acid is stronger.